So good day, everyone. Let's proceed to our fourth lesson, which is the topic strain. Okay, so introduction. So far we have dwelt mainly with the strength or load carrying capacity of our structural members. Okay, so we already discussed the topics axial stress, shear stress, and bearing stress. Okay, so we begin our study for equally important topics of mechanics of materials, mainly the deformations or strains. So in general, strain is a geometric quantity that measures the deformation of a body. So there are two types of strain. Normally, these are the normal strain, which characterizes the dimensional changes, and second is the shear strain, which describes the distortion or change in angles of a particular material. Stress and strain are two fundamental concepts of mechanics of materials. So their relationship to each other defines the mechanical properties of a material, so the knowledge of which is of the utmost importance in design. So axial deformation and the shear strain, so diagram. So the strength of materials is not the only criterion that must be considered when designing machines or structures. So the stiffness of a material is often equally important as are mechanical properties such as hardness, the toughness, and ductility of your material. Okay, so these properties are determined by laboratory tests. Okay, so many materials, particularly metals, have established standards that describe the test procedures in detail. So we will confirm our attention to only one of the tests, and this particular test is the tensile test of the steel, and use its result to illustrate several important concepts of material behavior. Okay, so we will first discuss the first type of strain, which is the normal or the axial strain. Okay, so before describing the tensile test, which will be discussed later, we must formalize the definition of normal or axial strain. So we begin by considering the elongation of a prismatic bar of length L in figure 2.1, which will be presented later. So the elongation with this is gamma, so may be caused by an applied axial force or an expansion due to increase in temperature, or even a force and temperature increase acting simultaneously. So normally these are the causes of those elongation. So there might be forces. Say this is your material, so there might be forces applied into the material. So this is in tension, okay, or pulling force. So meaning the elongation for this one is this is a stretch na stretch siya, meaning this will be stretch. Okay, so elongated. Okay, so the material will be elongated, while if the force applied is in compression, then this will shrink. Okay, so this will shrink, so you will have that particular deformation. So aside from forces, so there might be an increase in temperature. Okay, so it depends on the temperature if it is cold or hot. Okay, so that will also affect the elongation of the material. Or there might be tendencies that both the force and the temperature will simultaneously affect your material. So strain describes the geometry of deformation independent of what actually causes the deformation. So the normal strain, epsilon, is defined as the elongation per unit length. So given by this formula here. So epsilon is equal to uh, gamma over the length of the material. Okay, so therefore, normal strain in the bar of the axial deformation, also known as axial strain, is this is unitless. Okay, it's unitless. So if the bar deforms uniformly, then equation 2.1 represents the actual strain everywhere in the bar. Okay, so otherwise, this expression would be viewed as the average axial strain. So note that the normal strain, being elongation per unit length, is unitless. Okay, so this is the unit for that, or some uses inch per inch or mm per mm. These are the frequently used units for normal strain. So, however, if the deformation is not uniform, so we must define strain at a certain point of interest. Okay, so in figure 2.1, with this derivation, okay, so the point for this statement here is that when the deformation is not uniform, then we cannot directly use this formula. Okay, so since that is not constant. Okay, so if it is not uniform, then we will be going to use this formula here. Okay, so this is a general formula, which is the strain is equal to the limits of delta x approaching 0 is equal to delta elongation over delta x, or we could replace this delta with differential elongation over differential x. Okay, so observe that normal strain, like normal stress, is defined at a point in a given direction. So we note that if the distribution of the axial strain is known, so the elongation of the bar can be computed from, okay, so from this one. Okay, so the elongation should be integrated once the deformation is not uniform. Okay, so this will be the formula that we're going to use. Okay, so deformation is equal to integral of 0 to L d elongation, or equal to integral of 0 to L strain times dx. Okay, so meaning your strain should be in terms of x. Okay, so since the differential here is x. So for uniform strain distribution, so the axial strain is same at all points. So equation 2.3 yields deformation is equal to strain times L, which agrees with our equation 2.1. So ito siya. And this is our equation 2.1. Okay, so although the preceding discussion assumed elongation, so the results are also applicable to compression. Okay, so since our example here is all about this, say our P here is in tension, so this is in tension. So those formulas, this one, 2.1 and 2.3, are also applicable for compression force. Okay, so this is our sign convention wherein compression for the shortening, a shortening carries a negative sign. So say for example, if our epsilon strain is equal to negative 0.01, so meaning it has a compressive strain magnitude of 0.001. Okay, so for tension, then epsilon is in positive. Okay, so let's proceed to the tension test. So in the standard tension test, the specimen shown in 2.22 is placed to a grips of a testing machine. Okay, so there's a grip here holding both ends of the specimen. Okay, so these grips are designed so that the load P applied by the machine is axial. Okay, so the two gauge marks are scribe on the specimen to define the gauge length. So these 2 points here, okay, so these 2 points are your gauge marks, and the length, the difference of their length or the length between these two gauge mark is equal to L and considered as the gauge length. So these marks are located away from the ends to avoid the local effects caused by the grips and to ensure that the stress and strain are uniform in the material between the marks. So meaning this length L is the critical length for uh, critical length in getting the results for your stress and strain. Okay, so there's a cap here. Okay, so as you can see, there's a certain length of x. Say this is a certain length of x. So there's an allowance of length x there so that local effects of the grips will be avoided, and we can assure that the result will be uniform for both strain and stress. Okay, so the testing material or machine elongates the specimen. So as you can see here, it is being pulled with these P forces. Okay, then with a slow constant rate until the specimen ruptures, so until the material will mm, will be torn apart. Okay, so during the test, continuous readings are taken of the applied load and the elongation of the gauge length. These data are then converted to stress and strain. So the stress is obtained from this formula. Stress is equal to P over area, and strain is epsilon is equal to the elongation over the length. Okay, so these results, which are based on the original area and the original gauge length, are referred to as the nominal stress and nominal strain. Okay, so as the bars being stretched, its sectional area becomes smaller and the length between the gauge marks increases. So dividing the load by the actual area of the specimen, we get the true stress. So similarly, the true strain is obtained by dividing the elongation by the current gauge length. So the nominal and true measures are essentially the same in the working range of metals. They differ only for very large strains such as occur in rubber-like materials or in ductile metals just before rupture. So with only a few exemptions. Engineering applications use normal stress and strain. Okay, so those are the results for your uh, tension test. Okay, so plotting the actual stress versus the actual strain results in stress and strain diagram. So this is a very important concept for strain, a topic, normal strain. So if the test is carried out properly, then the diagram for given material is independent of the dimension of the test specimen. So that is the characteristics of the diagram are determined solely by the mechanical properties of the material. So stress and strain diagram for structural steel is shown in figure 2.3. Okay, so the mechanical properties can be determined from this diagram shown in the figure. So this is our stress strain diagram obtained from the standard tension test on a structural steel specimen. So our x-axis will be strain and y-axis will be our stress. So this is origin for our graph or for our diagram. So we have these properties here. So we have 5 or 6 points. So we have proportional limit as our first point. Then second point is the elastic limit. Then the third point would be our yield point. Then our fourth point is ultimate strength. Then we also have this nominal rupture strength. Then we have this dash line here if you wanted to carry out the true rupture strength. So let us define all of these properties mentioned in the diagram. Okay, so we have proportional limit. Okay, so when we talk about proportional limit, then it is being associated with Hooke's law. Okay, so as you can see in figure 2.3, uh, the stress strain diagram is a straight line from the origin O to a point called the proportional limit. Okay, so going back to the figure, so this is a straight line, guys. Okay, so this is a straight line here. Ito siya. So this is the only straight line, no, that you can notice, or you can notice in the diagram. Okay, so from point O, okay, from point O origin to that proportional limit, then that is a straight line. So this plot is a manifestation of Hooke's law. So stress is proportional to strain. So that is stress is equal to E times strain, wherein E is the material property known as modulus of elasticity or Young's modulus. Okay, so the units of E are similar with stress, wherein we are using Pascal or PSI. So this is a constant value, for example, for a steel material. So we have a E value which is equal to 29 times 10 raised to 6 PSI in US customary and 200 GPa for SI. So note that the Hooke's law does not apply to the entire diagram. It is valid, its validity ends at the proportional limit. So beyond this point, stress is no longer proportional to strain. Okay, so meaning at this particular area, so Hooke's law is useful in this point here in our graph. So beyond proportional limit, so Hooke's law is now invalid. Okay, so next, the second point, which is the elastic limit. So a material is said to be elastic if after being loaded, the material returns to its original shape when the load is removed. Okay, so that is the definition of elastic. Then the elastic limit is, as its name implies, the stress beyond which the material is no longer elastic. Okay, so beyond that point, okay, beyond this point here, so beyond this point, so meaning the material is not elastic anymore. Okay, so the permanent deformation that remains after the removal of the load is called the permanent set. So the elastic limit is slightly larger than the proportional limit. So however, because of the difficulty determining the elastic limit accurately, it is usually assumed to be to coincide with proportional limit. So meaning proportional limit and elastic limit is too close, okay, in the diagram. And then the third point would be the yield point. Okay, so this is the point where the stress strain diagram becomes almost horizontal and is called the yield point. And the corresponding stress is known as the yield stress or yield strength. So beyond the yield point, there is an appreciable elongation or yielding of the material without a corresponding increase in load. So indeed, the load may actually decrease while the yielding occurs. However, the phenomenon of yielding is unique to structural steel. Okay, so this is more, we are talking about yielding. That is more, that topic is more about structural steel. So other grades of steel, steel alloys and other materials do not yield as indicated by the stress strain curves of the material shown in the figure 2.4. Okay, so say this is a stress strain diagram of the material. As you can see, concrete, alloy, and cast iron usually does not yield. Okay, so the high carbon steel is normally the material that yields every time. So incidentally, the curves are typical for a first loading of materials that contain appreciable residual stresses produced by manufacturing or aging process. So after repeated loading, so these residual stresses are removed and the stress strain curves become particularly straight lines. Okay, so to our fourth point rather, which is the ultimate stress. So ultimate stress or ultimate strength, as it is often called, is the highest. Okay, so the highest stress on the uh, stress strain curve or the highest point as we can see here. So this is the ultimate strength. It's at the highest point. Then last is the rupture stress. So rupture stress or rupture strength is the stress at which failure occurs. Okay, so that's why rupture stress is the last point in our stress strain diagram because that would be the point wherein failure is being seen already. Okay, so for structural steel, the nominal rupture strength is considerably lower than the ultimate strength because the nominal rupture strength is computed by dividing the load at rupture by the original cross-sectional area. Okay. So the true rupture strength is calculated using the uh, reduced area of the cross-section where the fracture occurs. Okay, so that is a difference between the true rupture strength and the nominal strength, as you can see in the figure. Okay, so nominal rupture strength is has a smaller value than the true rupture strength because of that variation in area. The difference in the two values represent or results from a phenomenon known as necking. So this is the necking. Okay, so necking. So necking is also referred to as the narrowing, wherein the cross-sectional area of the specimen is decreased due to uh, due to the force pulled from the tension test. So as failure approaches, the material stretches very rapidly, causing the cross-section to narrow, as shown in this figure below. Because the area where rupture occurs is smaller than the original area, so the true rupture strength is larger than the ultimate strength. So however, ultimate strength is commonly used as the maximum stress that the material can carry. So normally the design, okay, most especially for civil engineers, so we design structures, specifically structural members such as columns, beams. Okay, so we design them using the ultimate strength. So the old code uses the yield strength only. Okay, but due to several studies made by our engineers, they carried out that ultimate strength is good enough to carry those stresses without failure. Okay, so ultimate strength. Then we also have the working stress and factor of safety. So the working stress or sigma W, also called as the allowable stress is the maximum safe axial stress used in design. So in most designs, the working stress should be limited to values not exceeding the proportional limit so that the stresses remain in the elastic range or the straight line portion of the diagram, if you could still remember. However, because of proportional limit is difficult to determine accurately, it is customary to base the working stress on either the yield stress, which is denoted as the sigma yp, or the ultimate stress or sigma ult divided by the suitable number n, or this suitable number n is also called as the factor of safety. Okay, so therefore to get the working stress that will be used in the design, the formula would be sigma w is equal to sigma yp over n, or ultimate stress over the factor of safety. And let's proceed to actually loaded bars. Okay, so for actually loaded bar shown in the figure 2.7, it has a length L, then a constant area of A. As you can notice, this is constant from the starting point to end point of the L distance. So we assume that the stress caused by P below is proportional limit, so that the Hooke's law, stress is equal to E times strain, is applicable. So because the bar deforms uniformly, so the axial strain is equal to deformation over L. So which upon substitute in the Hooke's law yields stress is equal to E times elongation over L. Therefore, we could create a formula for elongation of the bar, which is the elongation is equal to stress then times L over E. Okay, just simply cross multiply it, guys. So E times the elongation over L. Cross multiply L. So therefore, our deformation is equal to stress times L over E. But take note that stress is equal to P over area. So therefore, our formula for elongation could also be written as P times L over AE. Okay? Or similar or same with this formula here for 2.6. Okay, so that will be our equation 2.6. However, guys, if the strain or stress in the bar is not uniform, okay, so this formula is only applicable for uniform. Okay, applicable for uniform strain or stress. Okay, so if strain or stress is not uniform, then 2.6 is not valid. So in this case, where the axial strain varies with the x coordinate, so the elongation of the bar can be obtained by integration. Okay, so due with the non-uniformity of stress or strain, so we could simply integrate the formula. Okay, so we have elongation is equal to integral of 0 to L, then stress over E times dx, or pwede rin integral of 0 to L P over E A then times dx. Okay, so I think P is constant. The same with E. So maybe A. No, A should be a function of x. Okay, since the differential here is dx. So these are the notes on the computation of deformation. So the magnitude of the internal force P in equations 2.6 and 2.7 must be found from the equilibrium analysis. So meaning we could determine it using summation of x equal to 0, summation of y is equal to 0, or summation of moment is equal to 0. Okay, so equilibrium equations is useful in determining the magnitude of P. Then note that for positive P, so this denotes for tensile, and for positive elongation, okay, for positive elongation, that is being stretched, the material is being stretched. So conversely, in negative P denotes as a compression, which gives the rise to negative elongation, which is shortening. Okay, so there must be taken care to use the consistent units. Okay, so always take note of the units for your P, for your L, for your A, and for your E. Okay, so these are the common units used for those notations mentioned in the formula. And lastly, as long as the axial stress is in the elastic range, so the elongation or shortening of a bar is very small compared to its length. Okay, so there's no worry about it. So this property can be utilized to simplify the computation of displacements in structures containing actually loaded bars such as trusses. Okay, so let's proceed to our example. Okay, so for example 1, so the steel propeller shaft A, B, C, D carries the axial loads shown in figure A. So determine the change in length of the shaft caused by these loads. Okay, so given E, 29 times 10 raised to 6 psi. So this is our figure, guys. Okay, so for example 1. So first step is we'll be getting the value of P, or the internal forces for each segment. Okay, for each segment. So meaning, I think you can recall from the stress topic, no, so that in order to get the internal forces, then going to cut the shaft in a in a portion or in a segment. Okay, say this is your section 1 that is for AB. We have section 2 for BC, and that is for BC. Then section 3 for CD. Okay, so meaning if we consider section 1 section 1 then we will consider the force 2000. Okay, so 2000 pound. Then we'll be getting the P, no, the internal force on the other side. So I think this is 2000 as well. Okay, so that is for, or this is for segment AB. Okay, segment AB, so 2000. So PAB is equal to 2000 pound. Okay, so for section 2, this is for segment BC. Okay, so we will have this figure here. This is A, this is point A, guys, then this is point B. So for segment 2, we will consider the left side portion. So this is point A, we have 2000 pound here. Then this is for B, and also we're getting the force BC here. Okay, so I think this is also 2,000 pound. So PBC is equal to 2,000 pound. Okay. So lastly for section 3.3. Okay, so this is for segment CD. Okay, segment CD. So we'll consider the right side portion, guys. Okay, so right side portion, so meaning dito na portion. You could also consider the left side if you want. Okay, so to make the analysis easy, then we'll consider the right side. So this will be our point D. Okay, so we have a 4,000. Okay, so we have a 4,000 force here, which is in compression, meaning PCD will be equal to 4,000 pound as well. Okay, so therefore PCD is 4,000 pound. Okay, so this is in tension. The PBC is also in tension, then PCD is in compression. So expect a variation of a sign convention later. Okay, so because the actual force, okay, so you can see here the actual force and the cross-sectional area are constant within each segment. So the change in lengths of the segments can be computed from equation 2.6k, or meaning since the area is constant, then we could directly compute the change in length. So the change in length here is the deformation or the elongation of the shaft. This is total deformation or total elongation of the shaft. We could directly use the elongation is equal to PL over AE. So this is the formula that we'll be using. Okay, so since we have three segments, then uh, the deformation total is equal to summation of PL over AE. Okay, so we will sum up all the deformation for segment AB, okay, for segment AB, for segment BC, and for segment CD. Okay, so if we write it in general formula, uh, the value for E is constant, then we will let uh, 1 over E now outside the working equation. So 1 over E times PL over A. This is for segment AB. This is in positive now since PAB is in tension. Then plus PL over A. This is for BC. So again positive since PBC is in tension. Okay, and lastly, this is negative PL over A for CD. Okay, that is in negative sign since that is in compression. Okay, so substitute all the necessary values. So 1 over 29 times 10 raised to 6. Then times P 2000. Then times the L. Okay, so length for AB is 5 feet. Okay, so convert that into inches. So 5 times 12 inches. So to make the unit consistent, since 29 times 10 raised to 6 is in PSI, so mean that is pound per square inch. Okay, so over area. So the area, so we have diameter. So this is the diameter for AB. So 0.5 inch. So 0.5 inch, so that is pi by 4, 0.5 squared. Okay, so that would be the area for AB. Okay, then plus P for AB, BC. Now we are in BC, so 2,000. 2,000 pound, then times the length. Okay, so the length for BC is 4 feet. So 4 times 10, times 12 rather, then the area is pi by 4. Diameter for DBC is 0.75. So times 0.75 squared. Then minus P 4,000. Okay, so 4,000 then times the length. Again 4 feet for CD. So 4 times 12. Then over pi over 4 diameter 0.75 diameter CD. So times 0.75. Okay. So if you try to calculate this one, then the result or the total deformation is equal to 0.01358 inch. So this is in positive. Since that is in positive, therefore, the result will be elongation. Okay, the result is in elongation. Or the shaft is being stretched. Okay, so since the deformation is in positive. So once the deformation, say if the deformation is in negative, the result is negative, then this is shortening. Okay, so the result is shortening in that case. Okay, so that would be for number 1. So let's proceed to our last example. Example 2. So the cross section of the 10-meter long flat bar steel bar AB has a constant thickness of 20 mm. But the width varies as shown in the figure. So we are tasked to calculate the elongation of the bar due to the 100 kilonewton axial load. So use E is equal to GPA for steel. Okay, so the equilibrium requires that the internal force P 100 kilonewton is constant along the entire length of the bar, no, as mentioned here, 100 kilonewton all throughout the bar. So that would be the value for P regardless of the area. So however, guys, at the area, cross-sectional area of the bar varies with x coordinate. So that the elongation of the bar must be computed from equation 2.7. So meaning, since the area is not uniform, then elongation is equal to PL over AA. We cannot use that formula directly. So meaning we'll be using the formula with integration. Okay, integration is equal to 0 to L, then P AE, then times dx. So we'll be using this formula for this particular problem. Okay, so we start by determining, okay, so we start by determining the area as a function of x. Now, as you can see here that our equation is in dx. So how we could uh, determine this area there. Okay. So from the figure, so say this is the figure, guys. This is a figure. Then say this is the area or the area interest. Okay, so we could get the area here, okay, at this point, and we also have this particular area here. So say we will denote this as this is point A, then this is point B. Okay, so the area at A is equal to say since this is 40 mm, 40 mm, then this one is 120 mm. So meaning we have 40 then times 20. So 20 is the thickness of the material given in the problem. It's a constant thickness 20 mm. Meaning area at A is equal to 800 mm squared. Then for B, area B, this is 120 times 20. So area B is equal to 2,400 mm squared. Okay, so since the between A and B, okay, so between A and B, the cross-sectional area is linear. Okay, linear as a function of x. Okay, so since we have from A to B, this is 10 meters. Then for the point of interest for this area, say this is x. Okay, so this area is linear, so that would be a great analysis no, for us to determine uh, the value for a or a as a function of x. Okay, so what we'll do here is we'll be going to interpolate. Okay, interpolate in order to get this x. Okay, x as a as a function of x. Okay, so area AB. Okay, so area AB which is equal to 2,400. Then A. Then A okay, area at A. So which is 800 will be equal to the length. Okay, we consider the length. So say this is our datum. Okay, so our datum is at point A. So the 2,400 area for B is within the length of 10 meters. Okay, then from the datum, okay, from the point A to B, that is 10 meters, the area 2,400. Then this A area is x distance from our datum, which is at point A. So x, then 800 area is within the datum, so therefore the length there is 0. Okay, so by interpolation, okay, so by interpolation, so this is 2,400 minus A, then 2,000 over 2,400 minus 800. Okay, for the left side, then equate it to the right side term. So 10 minus x, 10 minus x, then 10 over 10 minus 0. Okay, so simplifying the equation, so we have 2,400 minus a, then over 1,600 is equal to 10 minus x over 10. Okay, so if we simplify it, cross multiply, okay, cross multiply, then we have for simplifying na lang the equation, so we could get a 2,400 minus a for the left side equation, then 160, then times 10 minus 8 minus x. Okay, so it becomes 160 here, since if we try to calculate 10 over 1,600, then the result would be equal to 160. Okay, then transpose, okay, transpose a to the other side. Okay, then also this equation to the left side. So therefore, we have a is equal to 2,400 minus 160 times 10 minus x. So simplify to 1400 minus 1600, 1600, then plus 160 times x. So therefore, A is equal to 800. 800 plus 160 x. So we have now this one area in terms of x. Okay, so using the equation, okay, so using this equation now, then we have elongation is equal to 0 to L, then P over AE dx is equal to 0 to 10, since our entire length is 10 meters, then P will be equal to 100 times 10 raised to 3. So this is in Newton now. Then our E is 200 times 10 raised to 9. This is in Newton meter squared. Then this area here this is in mm squared. So if we convert it into meter squared, then that would be equal to 800 plus 160 x times 10 raised to negative x meter squared. Okay, so we have 800 plus 160x, then times 10 raised to negative 6. So this is in mm squared. Okay, then don't forget dx times dx. Okay, so just review your calculus, guys. So just simplify this equation, okay, using the general integration rule, okay, that you have learned into your calculus. So the result for this one is 3.433 33 mm.